Okay, let's take a look at some more problems. If you're driving 60 miles an hour or 95 kilometers per hour and you look down at your phone for 2 seconds to check Facebook, how far do you travel during this inattentive period? Well, we know that there's a relationship between the average velocity and the change in position over the change in time. Using average velocity here because we're not accelerating. We're asked to solve for how far we're traveling, so what is this change in position? Well, if I multiply both sides by delta t, I'm going to get average velocity multiplied by change in time, or 95 kilometers per hour multiplied by 2 seconds. Now, you can kind of see I've written the units on here. The units are not going to cancel out. Here I have hours and here I have seconds. So I also need to say, well, I know that in 1 hour there's going to be 60 minutes and 60 seconds. You multiply the two of those together, you get 3,600 seconds per hour. So now my units are going to cancel out for hours. It's going to cancel out for seconds. And I go ahead and I multiply all this stuff together and I come out with 0.053, and the unit is going to be in kilometers. That's also going to be 53 meters, or roughly 150 feet. So you've traveled quite a long distance. So problem number 9 is making a distinction between speed and velocity. So here we have, say, a nice little track here, and we have a person. They're going to go around that track. They're going to do that 8 times, and we know the track is 400 meters long, so we know that the distance that they travel is going to be 8 times the 400 meter track, so they're going to cover 3,200 meters. That's going to be the distance that they travel. However, they're finishing where they're starting at, so their change in position is actually going to be equal to 0. Now, the average speed is going to be equal to the distance that you travel divided by how long it took you to do that. So that's going to be 3,200 meters, and we're giving our time as 14.5 minutes. Now we're asked to give the answer in meters per second. Here you see I'm going to have meters per minute, so I need to say, well, I need to go ahead and convert these units. I know that in 1 minute there's going to be equal to 60 seconds, so my average speed then, well, actually let me just show you that these units cancel out. I'm going to have minutes canceling here and be left with meters per second. So my average speed is actually going to be 3.68 meters per second. So that's going to be equal to my speed. Now my average velocity, so that's going to be that guy right there, that's going to be the change in position divided by the change in time. The change in position is going to be 0, and I have 14.5 minutes down here in the bottom. So the average velocity is actually going to be equal to 0 with units of meters per second. Now let's start taking a look at acceleration. The way I like to do these problems is have my equations of motion off here to the side, and the first thing I'll do is I'll write down everything that I know. So I know that the car is going to accelerate with an initial velocity, it's going to be v0 of 14 meters per second. It's going to accelerate to a velocity at the end of the day of 21 meters per second, and I know that the time that it took was equal to 6 seconds. I'm asked to solve for what is the acceleration equal to and how far did it go. So let's deal with first the acceleration. I look at my equations over here and I see that this top one, it's got the initial velocity, it's got the final velocity, it's got the time, and it has acceleration. So all I have to do is say, alright, well, I'm going to use this equation right here. First thing I'm going to do is I'm going to solve it for acceleration just to isolate the a variable. So I'm going to subtract v0 from both sides and say v minus v0 is equal to the acceleration multiplied by the time. Now I'm going to divide both sides by time, just like that. These times are going to cancel out, and I'm left with the acceleration is going to be essentially the change in velocity, v minus v naught, divided by the time. So that's going to be 21 is going to be the initial velocity, meters per second. V naught is going to be 14 meters per second. And then my time is going to be 6 seconds. So go ahead and I just peck all that into my calculator, and I'm going to come up with 1.167, and the unit will be meters per second squared, because on the top I have meters per second and on the bottom I have second. Now if you really want to write it with sig figs, you should probably only write it with two significant figures here, but I'll just leave it like that. So how far did the car travel in this time? So I go ahead and I look over here and I see, well, this equation right here has everything that I need to, or it has the final position at the end of the day already isolated right there. So to solve for this guy, I say, well, I'm going to take my initial position. I'm going to say my initial position is equal to 0, and I'm really looking for a change in position. So my position is going to be equal to the velocity multiplied by time, so v naught multiplied by t, plus 1/2 the acceleration, which I've just calculated, multiplied by time squared. So the initial velocity is going to be 14 meters per second. The time is going to be 6 seconds, plus 1/2. The acceleration is 1.167, and then the time is going to be 6. And that's, don't forget to square that, very common mistake. So at the end of the day, we're going to end up with 105 meters is how far it traveled. Problem number 24 is another problem with constant acceleration, just getting some more practice with these guys. We know that the, so again, here I have my equations of motion. I'm going to write down everything that I know here. So I know that the plane must reach a final velocity of 35 meters per second in order to take off, and I know that the plane is able to accelerate at a rate of 3 meters per second squared. I'm asked to solve for how long the runway needs to be, and I'm also going to say, well, I'm going to have to assume that the plane is going to start from rest, and I'll also say, well, my initial position is going to be equal to 0. Very typically that's what we do for these types of problems. So I go ahead and I take a look at all the equations that I have to play with, and really this one's going to deal with time, this one's going to deal with time, so probably I should just go ahead and use that guy. I suppose I could calculate time out and then apply one of those two, but why use the extra steps if I don't have to? So I'm going to first say that my initial velocity is equal to 0, and then my initial position, I'm also going to say that that's equal to 0. So I'm left with my final velocity squared is equal to 2 times the acceleration of the plane multiplied by the distance of the runway. Divide both sides by 2 times the acceleration, just like that. My 2 times acceleration is going to cancel out there, and I'm left with the position is equal to velocity squared divided by 2 times the acceleration. I know my final velocity is 35 meters per second. Make sure I square that guy. Divide that by 2 times the acceleration, which is going to be equal to 3. And I'm going to find out that my position should be 204.2 meters. Okay, here we have another acceleration problem. We're going to have a car that is initially traveling, so it's going to have an initial velocity, v naught, of 95, and it's going to have units of kilometers per hour. Now with any of these problems, typically we always want to work them in the SI system, so meters and seconds. So let's go ahead and convert these over while we're on top of it. I know that if I have 1 kilometer, that's going to be equal to 1,000 meters. And I also know that in 1 hour, I'm going to have 3,600 seconds. So my kilometer is going to cancel out, my hours are going to cancel out, and I'm going to be left with meters per second. And I type all that in, I come up with 26.39 meters per second. I have a few more decimal places, I'll just keep them in my calculator. I know that the car is going to come to rest. I know the final velocity that's going to be v, is now going to be equal to 0. I know the distance that it traveled is going to be equal to 0.8 meters, and I'm asked to find what the acceleration is. Similar to the last problem, this one is in time, this one's in time, so this is the one I probably want to go for. Now, I can also say that I'll always set my initial position equal to 0. So here I'm going to say, okay, that guy's equal to 0, and this guy's equal to 0, and I'm looking for the acceleration. So I'm going to first subtract v0 from both sides. I'm going to get negative v0 squared is equal to 2 times the acceleration multiplied by the distance that it traveled. Divide both sides by 2 times the distance that it traveled. Just like that. The 2 is going to cancel out. The x is going to cancel out. And I'm going to be left with the acceleration is equal to negative initial velocity squared divided by 2 times the distance that it traveled, or negative 26.39 meters per second squared divided by 0.8, and that's going to be meters. Since everything is in meters and everything's in seconds, my acceleration is going to come out in meters per second squared. It's going to be negative 435.2 meters per second squared. It asks, how many, so that's my answer right there. It asks for how, to write this in terms of g's, but actually first let me say, this answer is negative. What that means is it's slowing down. It's going from 95 kilometers per hour. It's going down to 0. Acceleration should be negative. It's in the opposite direction as the velocity. So, sorry about that. How many g's is this? We know that 1 g is, the 9.8 meters per second squared. That's the acceleration due to gravity. So, 435.2 meters per second squared, and I know that in 1 g that's going to be 9.8 meters per second squared. So I'm essentially going to divide that out. You can see that meters per second squared is going to cancel out, and I'm going to be left with 44 g's. So that's a lot of g-force. Now we have a problem where there is some acceleration, and this is now going to be the acceleration due to gravity. So here we have a ball, and this ball is thrown vertically upwards. It goes up, and essentially it comes back down, and the player is going to catch it in his hand pretty much at the same position. We know that the time elapsed is equal to 3.4 seconds, and we also know that the acceleration is going to be the acceleration due to gravity, which is 9.8 meters per second. Now I'm going to choose up to be positive. Acceleration due to gravity is always going to be downwards. Since it is in the downward direction, my acceleration is downwards, I'm going to say this is going to be negative 9.8 meters per second squared. I could choose it the other way around if I so wanted to. We also know that the ball is going to start and finish at the same spot, and I'm going to say this position is going to be equal to 0. So y and y naught are going to be equal to 0. First I'm asked for, how fast did he throw the ball, and I'm also asked for, what is the height did it reach, so what is the position at the top, what is that equal to? So first let's solve for the velocity. Taking a look at these equations, I don't think I have enough information here to solve it. I don't have enough information here to solve for the velocity, so I want to solve for that guy for the velocity. You can see I've changed my x's into y's just to say I'm talking about up and down now. I've said that my initial position is equal to 0. I've said my final position is equal to 0. I know my acceleration, I know the time, and I'm looking for the initial velocity. Get a v0 here. So I can say, well, if I subtract 1/2 at squared from both sides, I'm going to get negative 1/2 at squared is equal to initial velocity multiplied by time. Go ahead and I divide both sides by time just like that. Time's going to cancel out here. This is going to cancel out with one of those guys. And I'm going to say that my initial velocity is negative 1/2 acceleration multiplied by time, so negative 1/2 multiplied by negative 9.8 meters per second squared. The time is going to be 3.4 seconds. So I go ahead and I type all that in and I say, okay, my initial velocity is now equal to 16.66 meters per second. I'm asked for what height did it reach. I know something very important about the height. I know that the ball is going to initially have some velocity. It's going to be thrown upwards. The velocity is going to get smaller and smaller and smaller and smaller. It's accelerating downwards, so my acceleration is going to be in that direction. At the very, very, very tippy top, I know that the velocity of the ball is going to be equal to 0. It's still accelerating, but the velocity is going from being in the positive direction to being it now in the negative direction. So the velocity is equal to 0. So that's a key piece of information here. I'm looking for what height did it reach, so I'm looking for a position. I'm going to also say that my initial position is equal to 0. So I want to go ahead and use this equation right there. I know at the top that velocity right there is going to be equal to 0. I'm going to say my initial position is equal to 0, and I'm looking for this y guy right there. So I'm going to first subtract v0 from both sides. So negative v0 squared is equal to 2 times the acceleration times the height. Divide both sides by 2a. And go ahead and cancel these guys out. I can see that my y at the top is now going to be negative v0 squared divided by 2 times the acceleration, or negative 16.66 squared divided by 2 times negative 9.8 meters per second squared. And at the end of the day, I'm left with about 14 meters. Lastly, a problem with graphical analysis, very important tool to have in our bag. We're given a position versus time graph, and we know that the velocity is going to be the change in position divided by the change in time, or really what we're looking at is the velocity is going to be the slope of the position versus time graph. So we're asked what periods is the velocity constant. It says when is the slope of this guy constant. So the slope is going to be constant here. Slope is changing here. You can kind of see the slope is this tangent line that I'm drawing, and now this slope is going to be changing everywhere else up. So from about 0 to, I don't know, maybe about 18 or so, the slope is going to be a constant value. So from 0 seconds all the way out to roughly 18 seconds. It asks for when is the velocity the greatest, saying when is the slope the largest. So we can draw our little slope lines. The slope's going to get larger and larger, and then it's going to get smaller. It's going to touch 0, and this is going to become negative just right there. So the largest slope is going to be right about here. So we can say, I don't know, about 27 seconds, give or take. It's going to be the largest slope, the largest velocity. I've already answered the next part. Here we're going to have a positive slope. Here we're going to have the largest positive slope. Here we're going to have a slope of 0, and here we're going to have a negative slope. So when is the velocity 0? When is the slope of the position versus time equal to 0? Roughly 38 seconds. Now it asks, does it move in one direction or both directions? Well, here it has a positive velocity. Here it has a 0 velocity, it's essentially stopped. And here it has a negative velocity, so it's traveling in the opposite direction. So it is going to move in both directions.